The Doppler effect. The Doppler effect is the apparent change in a frequency of a wave motion as noted by an observer when there's relative motion between the source and the observer. What does this really mean? It's just saying that you're going to hear a difference in frequency whether you're moving or whether the source is moving when you hear a sound. This effect is caused by the motion of either the source, the observer, or both. If there's a moving source, then what you actually are observing is the wave crests that are bunching up in front of the source and the wave crests that are more widely spaced behind the source. And the overall effect is to cause a change in wavelength. And the wave speed is not affected because that only depends on the medium. So if the observer is moving, then you get an apparent change in wave speed. I say that there's no actual change in wave speed, but you get an apparent change because of the observer moving. There's no change in wavelength, but the observer does appear to see more waves per second, which means that they get an increased frequency, which is why it's a higher pitch. And if it's moving away, then you get a decreased frequency, so less waves per second. If you have a stationary source with an observer, the source just radiates sound and the observer will hear a constant frequency. Your wavelength is constant and your frequency is constant. Your wavelength is basically the distance between these pink lines. I wanted to point that out because in your next slide, when you actually start to get a source that's moving, for example, towards an observer, then as the source moves, the distribution of the waves goes with it. And so you can see here the wavelength is smaller, whereas here on this side the wavelength is larger. So you get a reduced wavelength for the observer, which means there's an increased frequency. Now what happens if the source is moving away from the observer? Same thing happens, but this time the observer is on the other side. You can see that they see a larger wavelength and a smaller frequency, meaning a lower pitch. What happens when an observer is moving towards the source? Then it meets more waves per second. So it's kind of like the source moving towards the observer, but in this case the observer is moving towards it. And that means that the effective velocity of the waves is increased. I say effective velocity, the velocity is not increased, it's just the effective velocity. Same thing happens when the observer is moving away. It receives less waves per second and the effective velocity of the waves is reduced. This gives us a way of describing the differences in these things. Well, if the source and the observer is moving, then you get a combination of both of these. So you get both the wavelength and the effective wave velocity being changed. So if you consider a source that is emitting sound or light with a wavelength of lambda, then the time for one wave to be emitted is the reciprocal of the frequency. So it's just the period, which is 1 over f, and that's lambda over c. So if we remember that c here is the speed of light, so 3 by 10 to the 8 meters per second. If the source is moving away, or have moved away from the observer a distance of how many meters during the time that it takes for one wave to be emitted. So distance is equal to velocity times time, so it just means that the distance it travels is the velocity times lambda over c. So that gives us an expression for the change in wavelength. Change in wavelength is v times lambda over c. And the fractional change in lambda is then just this relationship, it's a ratio. So this is the ratio between the speed of the wave and the speed of the observer, or the speed of the, as long as the speed is much, much less than the speed of light. When it gets close to the speed of light, funny things happen. So this fractional change in frequency can be given by a similar formula, where you get a change in frequency that's just the relationship between the speed and the speed of the wave. So if the source is approaching, you get identical changes in wavelength and in frequency. If it's not approaching, then you might have to use a combined equation. So in this case, we've got a combined equation here that looks at the frequency, and you can have the speed of the wave is v, and the speed of the detector, which is the observer. So if the source is stationary, this one here is 0, and the observer is moving away, then it could be positive. And so you're moving away, you're going to hear a lower frequency. If your observer is moving towards, then you're going to hear a higher frequency. So you can be careful about how you put in the pluses and minuses here. This can be a plus minus on here and a minus plus on the bottom, depending on which direction, whether it's going towards or behind. Here's another way of looking at it from the Hyperphysics website. The Doppler shift can also be observed in light. So you get a red shift when the colour, so a red shift means that you've got something that's moving into the red region. And that means that you're getting a relative motion between the source and the observer. If it's a red shift, it's moving away. And the emission and absorption lines of the distant stars and galaxies show this red shift compared to the similar elements in our laboratory sources. This red shift is due to basically the motion of the stars and the galaxies in our solar system moving away, suggesting that the universe is expanding. But some of them, for some of the close stars, we might actually see a blue shift, and that's because the rotation of the galaxy is close to us. So, blue shift, red shift. How does it actually look on your spectrum? So here's a continuous spectrum, and if you look at your hydrogen spectrum from a hydrogen source, that's what it would look like. But a red shifted spectrum is shifted into the red, just out of that region. Blue shifted spectrum would be in the opposite direction. What sort of applications does it have? Well, you can look at different things like the rotation of the sun or rotation of the planets, rotation of Saturn's rings, rotation of galaxies or recession of galaxies. You can even use it to look at the origin of the universe.